All right, so today we're going to talk about October 6th material, which is the fundamentals of counting, and this is going to start the Combinatorics section of our course. So the first thing we're going to look at is, say you have a bunch of sets and you collect them all together, what is their size? So if S1, S2 up to SK are sets, their union, this is actually something we talked about before, is the set that contains all of the elements in it. So it's the set S1 union S2 union up to all the way to SK, which is the set of elements X such that X is in one of these sets Si. So it's an Xi for some I. Okay, let's look at an example. So say you had this set S1, which consisted of the elements ABC, S2, which consists of EF, and S3, which consists of GHIJ. What is the size of the union? Well, you notice that all of these sets S1, S2, S3 have nothing in common. So in fact, the size of the union is going to be 9. Right? And this is because of the fact that these are disjoint. So this is the size of S1 plus the size of S2 plus the size of S3 because S1, S2, and S3 are, I'm going to use this term, pairwise disjoint. Disjoint means that sets have nothing in common, and pairwise means every pair. So every pair is disjoint. These two have nothing in common, these two have no elements in common, and these two have no elements in common. So we can see this kind of would generalize, and I won't give a proof here, but we'll at least write this down. If S1 through SK are disjoint sets, then the size of S1 union S2 union all the way up to the union of SK is equal to the size of S1 plus the size of S2 plus etc. up to the size of SK. You could, if you wanted to, actually prove this using mathematical induction, where you prove it for two sets first, and then think about this whole thing as the union of S1 and this entire set, which uses more sets in the union. Now, we're going to actually get a formula for a union like this where the sets might intersect. We'll talk about that a little bit later. And that requires looking at those intersections and taking care of situations where you have overcounting. But that's something we'll come to later. So this thing is sometimes called the sum rule for counting. And there is a similar rule which has to do with looking at lists of elements, and we'll see that on the next slide. So if S1 and SK are S1, S2 up to SK are sets, their Cartesian product is defined as follows. It's the set of all pairs or all k-tuples, where the ith coordinate comes from the ith set. So it's hard to distinguish here between the capital S's and elements. So I'm going to make that a little bit more explicit. So it's capital S1 cross capital S2 cross capital all the way to capital SK. And it's the set of tuples that look like S1. I'm going to put a tilde on top, S2 tilde, up to SK tilde, such that SI tilde is an element of the I set for each I. Now this is sort of a little bit of a formalism here, but you can think about this as lists of k elements where the ith element is coming from the ith set. So for instance, suppose that we had S1 being ABC and S2 being FG, then this set S1 cross S2 is a set where you select some element for your first coordinate, it could be say A or B or C, and then select another element for your second coordinate. Maybe you select F in each of these cases. And then same thing with the second coordinate, changing from F to the other option that you have. Okay, so these are all ordered pairs. And so we can think of these then as ordered K tuples. And a fundamental principle of understanding these things has to do with recognizing what their size looks like. So if you take a look at this, this set has size 3, and this set has size 2, whereas this set of ordered pairs has size exactly 6, which happens to be the product of these two. And that's the rule in general. If you have sets S1 through Sk, then the number of ordered k-tuples, where the ith element or ith coordinate comes from the ith set, has size equal to the product of the sizes of the individual sets. And you can kind of see an argument for this. For example, if you were looking at just S1 cross S2 for finite sets S1 and S2, then you have 3 choices for the first coordinate in this example. In general, you would have size of S1 many choices for the first coordinate. And for any particular choice of the first coordinate, for example, if you choose A, you have exactly size of S2, in this example, 2 choices for the second coordinate. So if you pair things up based on their first coordinate being the same, the number of pairs you'd have is exactly the size of the second coordinate. And so overall, you'd have the size of S1 times the size of S2. And then you can imagine establishing this inductively as well. So let's look at an example of how something like this framework would actually help us in terms of counting. So let's look at our first counting problem. How many 6-digit license plates can be made if the first 3 digits are even numbers and the last 3 are prime numbers? And remembering that these 6 digits are each between 0 and 9. So we should be a little bit more explicit here. The last 3 are each prime numbers. So they're each 1-digit numbers that are prime. So I'll create 2 sets here. One for the first 3 digits, I'm going to call that S. So I'm going to let S be the set consisting of all the even choices, which is the set 0, 2, 4, 6, 8. And then I'm going to let P be the set that contains all the prime numbers. So those are 2, 3, 5, and 7 as digits. Okay, so then what we notice is that valid license plates are lists, in fact, ordered lists. Lists are typically ordered, so I'll just emphasize this, lists. Meaning ordered of 6 digits the first 3 from S and the second 3 from P. Okay, well, what is this? This is precisely the set that's the Cartesian product S cross X cross S cross P cross P cross P is all 6 tuples of elements, the first 3 coming from S and the last 3 coming from this P right over here. So we can tell what the size of this is by our counting formula. So by the product rule, the size of S cross S cross S cross P cross P cross P is equal to the size of S, size of S, size of S, size of P, size of P, size of P. Okay. S has 5 elements, so there's a 5 cubed. P has 4 elements, so this is 4 cubed. And this is 20 cubed, which is 8,000. So we don't have to list all the possibilities and make guesses of any kind. We can directly recognize that the 6-digit license plates form this Cartesian product. So the number of them is exactly 8,000. Okay, so these are 2 fundamental counting principles that come up time and time again. And we should have a general formula for counting things using this phenomenon. So we're going to start by thinking about this idea of lists explicitly, and then moving from there. Okay, so some notes. In the product rule for counting, the elements in here, there's actually times over there, are often called lists. And the reason they're called lists is because they consist of ordered pairs, right? The fact that you have these tuples give you a sense of which ones are coming in which order. If it happens to be the case that all of the sets that form the Cartesian product are actually the same, say all of them being the set A, then this Cartesian product of the K sets, because all of the sets are actually A themselves, is usually abbreviated as A to the K and consists of K element lists of from A. So as an example, I want to make this actually very concrete and relevant to something that you may have seen before. In linear algebra, you often talk about vector spaces like R3. Well, what does that really mean? This is actually, from a linear algebra point of view, the set of triples A, B, C, where A, B, and C are all real numbers. But now if we look at this in the context of what we just talked about, this is precisely R cross R cross R. It's ordered triples, each coordinate of which is coming from the real numbers. So instead of writing R cross R cross R, we usually just write R cubed. Okay, so if A is a set with n elements, how many K element lists are there with each element in the list coming from A? Well, K element lists from A are precisely the elements of A cross dot 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 cross A, where we have K copies of A, meaning exactly A to the K. Okay, so K element lists from whose elements are in A are precisely, they're exactly elements of a to the k. So our question then is, what is the size of this? Well, by the product rule, the size of a to the k, this is the size of a cross, etc., cross a. We have k copies of this. All right, and so this is going to equal the size of a raised to the k. And a has n elements, so this will have n to the k elements in total. So a nice way to see how to develop a formula like this, number of k element lists coming from a particular finite set with n elements, is precisely n to the k. Let's look at a concrete example so that this is put into some kind of context that feels real. How many possible outcomes are there when one rolls 5 6-sided dice? And the dice themselves are considered different. So I'll draw a picture to give you a sense of what it is we're talking about here. So if you have a die, typically it has something like a number on a face between 1 and 6. So 6 is opposite of 1. You might have something like a 3 and then maybe a 2 up top here. Okay, and this number on top is the roll. Okay. And so there's 6 possible outcomes for a given roll. Let's actually record this. So each die has 6 possible face values. I guess I'll use the term face values. And they're the numbers 1 through 6. Okay, so if you roll 5 dice, they're considered different. You'd have an ordered set of 5 dice. So the possible outcomes of rolling five dice is precisely the set d to the 5. Again, I like to make this more concrete. Let's put an example here, maybe in gray. What's the example? Here is an element of d to the 5, and this is telling you the rolls. This is the first roll. The outcome of the rolling the second die, etc. Okay, now we know what the size of this is. The size of this, by what we just said earlier, is the size of d itself, which is 6 raised to the 5. So this has size, the size of d to the 5, which is 6 to the 5. Okay, great. So we're starting to be able to do some counting of this kind. Now we'll make things a little bit sophisticated by introducing the ability to move objects. So the first example of such a thing we're going to talk about is permutations. So a permutation of a list is the set of, let's just say the set is the set of all possible rearrangements of the list. So for example, here is a list ABC. One possible rearrangement is to keep things static. That's usually called the trivial rearrangement. Then you could do something else. You could swap the roles of A and B, or B and C, sorry. Then you can make B first and have A and C come afterward in that order, or you can choose C to be present first. Then finally, there are two choices where you let C be the first element. So a question is, how many ways can you actually rearrange objects? So how many permutations are there of a list of n distinct objects? Okay, well, let's think about it this way. Think about filling in a given permutation of n objects. So first of all, there are n options for the first element of a permutation. For example, if you are permuting ABC, then you can either put A first, or B first, or C first. Now, no matter which of these you decide, no matter if you decide A first, or B first, or C first, the number of options you have left for the second coordinate is exactly 2. It's the 2 other elements of your list that you have not selected to introduce in your rearrangement yet. For example, if you pick A to be the first element, then either B or C is the second. If you pick B instead to be the first element, then either A or C is the second. So there are n minus 1 options for the second element. Okay, independent of the first element chosen. Okay, this gives a total of, we have n elements for the first coordinate and then n minus 1 subsequent ones no matter which first one you pick. So this gives a total of n times n minus 1 possibilities for the first 2 coordinates. And the reason for n minus 1 here instead of n for the second coordinate is the second coordinate has to be distinct from the first one. So you can imagine what follows. In a general setting, if you wanted to know how many, once you've selected the first and second coordinate, how many ways there are to select the third, you have n minus 2 options for that. And then the question becomes, how many permutations or how many ways are there to fill the first 3 entries? It'll be the number of ways to fill the first 2 entries, which is this, times n minus 2, because the number of ways to fill in the third entry does not depend on which of the first 2 you selected. Okay, so then you'd get n times n minus 1 times n minus 2, and you can imagine continuing in this fashion until you run out. So continuing in this fashion, the total is n times n minus 1 for the number of ways to pick your second element for a fixed choice of the first one, then times n minus 2, where we've selected our first 2 elements and wonder how to fill in the third, And you keep going until you run out of things, giving you a total of n factorial. So the number of permutations of n objects in total is n factorial. Now we've actually answered a question that goes above and beyond this, and I want to see that through a particular example which you can argue generalizes. So instead of permuting an entire set, what if we ask something like this? How many k element lists are there consisting of k distinct elements from a chosen fixed n element set? It's a lot of words. So let's start with an example. Say n was 7 and k was 3, right? So you're selecting, it's equivalent to selecting a 3 element list from this n element set right here. Okay, so in the same light as what we did before, we have 7 ways to select the first element in the list. Okay, once that's done, we have 6 ways to select the second element in the list. But this is independent of the choice of the first. Okay, and then once we've selected the 2 first elements, we get that the ways to select the third element in the list is independent of whatever you chose for the first 2. Okay, I should say 5 ways. So what does that give you as a total then? It gives you 7 times 6 times 5. So the 3, or the 7 is telling you where this starts, and the 3 is telling you how long it goes. So you can imagine having a very concrete proof of this, that in general, the number of k element lists, distinct lists, list of distinct elements chosen from an element set is n times n minus 1 times etc. times n minus something. There are 3 elements here. This is not n minus k, it's a little bit more, because this list has exactly 3 elements, and we start with n minus 0. So we have n minus 0, n minus 1, all the way to n minus, not k, but the quantity k minus 1. Okay, and there's a nice convenient way to write this that will be useful for us in the future. So the convenient way is to continue with this factorial looking writing. We notice we're starting with n and descending in the products. The next element that would arise is n minus k. And then we'd have n minus the quantity k plus 1. And then this keeps cascading down until we're left with 3, 2, and 1. But you can't, in mathematics, just introduce any type of factor that you want. You have to be able to balance this out. And so we'll do that by dividing by this contribution in the denominator. And once we do that, we notice that this is equal to the numerator being n factorial, the numerator being n minus k factorial. So unlike what we had in the previous iteration, the number of k element lists where you don't care whether or not you have repetition is n to the k. But if you want a distinct ordered list, it's going to end up being this number, which was motivated by this example, which can be rearranged to this nice compact factorial form. So that's a start to our counting principles. In the next class, we're going to go over some strategies for actually counting in more complicated scenarios.